Hey, time for more fun with logs. This is going to be the end of section 5.2, log functions and their graphs. And today we're going to talk about the natural logarithmic functions. Remember, we had the natural exponential that was e to the x. This is sort of the reciprocal of that, or the inverse of that. We had our natural exponential, or base e. Now we're going to have the natural logarithm. By looking back at the graph of the natural exponential function introduced in earlier in this chapter in section 5.1, you'll see that f of x equals e to the x is 1-to-1, so it does have an inverse function. This inverse function is called the natural logarithmic function and is denoted by the special symbol lnx, which is read as the natural log of x, or the ln of x, just like you're naming it by its letters. We have L, we have N, the ln of x. Note that the natural logarithm is written without a base. The base is understood to be base e. So you know it's the same as, but you never see this, the log, log base e. But they just call it the ln. And there is no base because that would be the ln of e. So in the blue box, the natural logarithmic function, it's defined by fx equals log base e of x, which is the same as the ln of x, with x being positive. And this is our natural logarithmic function. The definition above implies that the natural logarithmic function and the natural exponential function are inverse functions of each other. So every logarithmic equation can be written in its equivalent exponential form, and every exponential equation can be written in logarithmic form, where that is, y equals ln of x and x equals e to the y are equivalent. Because the functions given by fx equals e to the x and g of x equals ln of x are inverse functions of each other, their graphs are reflections about the line y equals x, and that is illustrated here in this picture. So the light gray is the exponential. Here's our e to the x function. It crosses at 1, 0, and it has the point 1, e and -1, e to the -1 power. Now our natural logarithmic function, or the ln of x, is here in the darker black. And it is a reflection about the line y equals x. So here is our y-intercept, 0, 1. Here is our x-intercept, 1, 0. This point was 1, e. Now its reflection is e, 1. And the same thing for -1, e to the -1. Now we just reverse those coordinates. E to the -1, or 1 over e, -1. So this is our natural logarithmic function, or the ln of x. On most calculators, the natural logarithm, or the logarithm, is denoted by, you should have a button with just ln on it. So in example 8, we're going to just do a little calculator work here. Use a calculator to evaluate the function given by f of x equals the ln of x for each value of x. So we're going to plug in the 2 and take the natural log of that, and 0.3 and take the natural log of that. And then we have this one, the quantity, 1 plus the root of 2, and we'll take the natural log of that. So let's see here, if you plug in 2 and hit the ln key, you should get an output of 0.6931472. The decimal, 0.3, and hit the ln key, and you should get negative 1.2039728. Plug in a negative number, -1, hit the ln button, and you're going to get an error. And it says here at the bottom in example 8, be sure that you see that the ln of the -1 gives an error message on most calculators. Some might display a complex number. This occurs because the domain of the ln of x is the set of positive real numbers. So for the ln of -1, it's undefined. The last one, if we do 1 plus square root 2 equals, and then take the natural log of that, you'll get 0.8813736. Just like the regular log, the logarithms had some special properties. Natural logs have very, very similar properties. The ln of 1 is equal to 0, because e raised to the 0 power, or anything to the 0 power, is going to equal 1. The ln of e itself is equal to 1, because e to the first is equal to e. The ln of e to the x is equal to x, and the e raised to the power ln of x equals x. That's because the ln and the exponential are inverse properties. And here's number 3, the ln of e to the x. Well, inverse properties, the ln and the exponential are going to cancel each other out, so we're just left with the exponent x. And if we have e raised to the power ln of x, well, they are inverse properties. E to the natural log are going to cancel, and we're just left with x. And of course, we do have a one-to-one property there for number 4. The ln of x is equal to the ln of y, so x equals y. One-to-one property. All right, let's see. It says use the properties of natural logs to simplify each expression. Let's move these up so we got a little more room here. So letter A, we have the ln of 1 over e. Well, let's rewrite that 1 over e as a negative exponent. Down here it's e to the first. Bring it up, it's e to the negative 1. Now we can apply one of our properties. The ln and the exponential are inverses, so those cancel, and our answer is just negative 1. Letter B, we have e raised to a power, and part of that power is the ln of 5. Well, the e and the ln are inverses, those will cancel, so we're just left with 5. Letter C, the ln of 1 over 3. Well, what's the ln of 1? 0. Divided by 3, 0 divided by anything is 0. Okay, last one. 2 times the ln of e to the first. Well, the ln of e, those cancel. They're inverse operations, so we're left with the 1. 2 times 1 is 2. Easy as that. In example 10, it says find the domains of the logarithmic functions. So let's see here in the first one, we have the ln of the quantity x minus 2. And remember from the previous video, this minus 2 in here is going to shift everything to the right 2 units. So we're looking for the domain. Our domain used to be for just the ln. For the natural log, our domain is 0 to infinity. Now this minus 2 has moved everything to the right. So our domain, or our asymptote, is not going to be the y-axis anymore. That asymptote has been moved 2 units to the right, so our asymptote is now 2. So here our domain is also going to be moved 2 units, from 2 to infinity. And notice I did not use a square bracket here. That would mean that 2 was part of the domain. 2 is the asymptote, and we're never going to touch it. So we need a parenthesis. 2 to infinity. Let's see what we have next here. Letter B. G of x equals the ln of 2 minus x. So we're sort of flipping our graph around the line x equals 2. So here's our line x equals 2. The ln graph usually looks like this, up and to the right increasing, but now we're going to shift that and reflect it here to the negative, or the left side of our asymptote. So what is our domain going to be? Well, it's going to be all the numbers between negative 2 and negative infinity. And the last one, the ln of x squared. Different kind of function looking here. So if we graph that, we're going to have the ln of x squared going this way. And when we plug negative numbers in, if we plug in the negative 2, this is x squared. If we plug in negative 2 and square it, we're going to get a positive output. And we can take the ln of 4. So we're going to have another graph that is the reflection of the first, but now we're heading off this way. So what is our domain going to be? Well, if we go from the y-axis positive, we're going to go from 0 to infinity, but not 0, because that again is our asymptote. And for the other half of the graph, we're going to go from negative infinity to 0 and not touch the 0 again. So we could have these two pieces with a union symbol in between them, or an easier way to write that would be the set of all x's such that x does not equal 0. Any other number is fair game. Positive or negative are fine. We just can't put 0 in because the y-axis is our asymptote. Example 11, there's nothing really to write down in it. I just wanted to make sure to include this because this is a real-life application of where would people use logarithms in a career or in science. So, students participating in a psychology experiment attended several lectures on a subject and then were given an exam. Every month for a year after the exam, the students were retested to see how much of the material they remembered. The average scores of the group are given by the human memory model. F of t, remember t is time, f of t equals 75 minus 6 times the natural log of t plus 1, where t is the time between 0 and 12 months. So, what was the average score of the original, or t equals 0, exam? What was the average score after 2 months? What was the average score after 6 months? So here's our solution. So we plug in 0. At time 0, 75 minus 6 times the ln of 0 plus 1. Well, 0 plus 1 is 1, and the ln of 1 is 0, so 6 times 0 is 0, and the average score is just the 75. So what happened after 2 months? Did the kids get smarter, or did they stay the same, or did they forget some stuff? So we plug in 2. After 2 months, it's now 75 minus 6 times the quantity, ln of 2 plus 1, or the ln of 3. We take that, multiply by 6, subtract from 75. Now the average score was about 68.4. So we dropped, and that's to be expected. 2 months after you hear something, you are not going to remember all of it. Scores dropped a little. After 6 months, we plug in 6 for the variable x. So 6 plus 1 is 7. The log of 7 is 1.9 times 6, and we subtract that to 75. Now the scores dropped, about 5 more points. We went from a 68.4 to a 63.3. As time passes, you're not going to remember as much. It just makes sense. And the best way to model this type of graph is with a logarithm. We could, graph that on our TI-89, use the graphing utility. We could graph that on there, and then we could use the value or the trace feature to approximate, any time we wanted to plug into that in for x. So time for a few practice problems. In the first one here, number 67, use a calculator to evaluate the function, round to 3 decimals. In the next one, 71, find the x, or find it at the evaluate g of x equals the natural log of x at the indicated value of x without a calculator. So the ln of x, you're just going to plug in for x, e to the 5th power. The ln of e to the 5th, simplify it without a calculator. For number 75, find the domain, the x-intercept, and the vertical asymptote of that logarithmic function, and sketch the graph. That's just going to be a shift. So pause the video, try the problems, start her back up, and see if you got them right. Okay, let's see here in the first one. We're taking the ln of x when x is equal to this. So we want the ln of 18.42. And I haven't tried this on my computer calculator yet. Okay, I got to put the number in first. So we need 18.42. 18.42, and we want the ln of that, so here's our natural log button, and they want us to round to 3 spots, so 2.913. 2.913. For 71, evaluate the g of x equals the ln of x at the given function, so we want to take the ln of x when x is equal to e to the 5th. Well, let's see. The natural log and the exponential are inverses. They cancel each other out. So our answer is 5. And the last one. Let me move this up so we have a little more room here. Get some of this out of the way. Make my graph a little bit bigger. And we're not going to need the whole graph. Let me move it over here so we can just see the part we're going to need. And we want to graph the ln of x minus 4. So let's see, the ln of x would look something like this, roughly. Oop, that's a terrible asymptote. I can't let that stand. We're going to fix that up. Oh, that's even worse. So one more, third time's the charm. I'm going to come down like this and approach that y-axis but never touch it. So ln of x minus 4. That minus tells us we're going to go in the opposite direction to the plus side. So my intercept is not going to be at 1. We're going to move that over to 4. And that means this upper part of the graph will move over, as will the lower part of the graph. So they want us to find the domain. Let's see, domain. The domain is usually 0 to infinity, but everything got shifted over. And it got shifted over 4 spots, and actually I should have went over farther. My x-intercept was 1, 0, and that got moved over 4 units, so that should now be over at the 5. At the 5. Everything got shifted over 4 units. I can't believe you didn't stop me. You know, our x-intercept was usually at 1, and everything got bumped over 4 units. So 1, 2, 3, 4, we should be at our x-intercept at 5. So our domain is usually from 0 to infinity, but everything got bumped 4 to the positive, so now it's 4 to infinity. X-intercept. Our x-intercept is usually 1, 0. But again, everything got shifted over 4 units, so we add 4 to that and get 5, 0. The last thing is the vertical asymptote. Vertical asymptote is usually the y-axis, but that got shifted over 4 units to the line x equals 4. And there we go. Homework for this section, 30 to 32, 48 to 50, and I do have a handout worksheet. So make sure you get that from me.